All right, so I'm going to talk about one possible way of deriving one-step methods, which are referred to as Runge-Kutta methods. So it's very natural then, as we talked about, to apply quadrature rules to approximate the solution to an ODE, right? And of course, it's like the idea behind this is, of course, from the fundamental theorem of calculus. So from the fundamental theorem of calculus, you have that the solution at the new time is equal to the solution at the old time plus the integral from Tn to Tn plus h of the vector field evaluated along the solution trajectory. Okay, and of course you can replace this integral by some sort of quadrature approximation. So you could imagine by approximating the integral with a numerical quadrature rule. What you get is that the solution at the new time minus the solution at the old time is equal, or can be approximated by some quadrature approximation. All right, and so here it's like I'm going to drop the time dependence of the vector field. And okay, so if you look at a formula like this, one of the real problems, of course, is that you don't actually know it's like this y as a function of time, because that's one of the things which you're trying to solve for. So, so the problem, of course, is that the quadrature rule requires you to know something about the solution y at these quadrature times. Okay, so the problem is that we don't know the intermediate values which are y at Tn plus CIH. Okay, so, and of course this is true for I equals 1 to s. Okay, so so what essentially happens then in a Runge-Kutta method is that you again write down an expression for y at Tn plus CIH. It's like in terms of a netted quadrature formula. So in principle, nothing prevents you from applying the fundamental theorem of calculus to this quantity here, right? So you could imagine that you write y at Tn plus CIH, if you will, as y at Tn plus the integral from Tn to Tn plus CIH f evaluated y tau, tau d tau. Okay, so so what that naturally suggests then is that you could again approximate now this integral over a different time interval, again with some sort of quadrature formula. All right. So let's see what that kind of reasoning leads to. Okay. So in a Runge-Kutta method, it's the final update, y at n plus 1, is going to be written as yn plus h times the sum from I equals 1 to s of bi f evaluated at some internal stages, which I denote by yi. And the idea basically is that yi should be viewed off as an approximation of y at Tn plus CIH. Okay, and the problem remains, about how you compute, it's like these yi's. So these yi's, okay, as I said, are approximations of Tn plus CIH. So they themselves, it's like can be approximated by some sort of quadrature approximation. So we write this as Yn plus H, sum of some quadrature rule, where the quadrature weights now depend on both the i's and the j indices. So you have basically aij f evaluated at the yi's, again, yj's, I'm sorry. Okay, so so the idea is that you have quadrature weights, but again, the quadrature points are the same points. So that sort of allows you then, in principle, to have a closed system of equations. All right, so let's just look at this for a second. Okay, so you have I equals to 1 to s. Okay, so if you look at this expression, y at new time is equal to y at the old time plus some weighted combination of the vector fields at what are called the internal stages. So these are called the internal stages. And then the internal stages themselves, it's like satisfy a very similar type of equation, but with different quadrature weights, aij. But what you notice again is that the quadrature points are the same, and that's to prevent you from introducing additional unknowns which you don't know how to deal with. Okay, so so let's look at what you know and what you don't know. The unknowns here are the new solution, y at n plus 1, as well as the internal stage values yi, where I is allowed to vary from 1 to s. Okay, so they're basically s plus 1 unknowns. All right, but you have s plus 1 equations, right? You have the equation, it's like for yn in terms of some weighted combination of the vector fields, as well as these equations, which the y's, i's have to satisfy. So the s of these equations plus 1, you have s plus 1 equations, s plus 1 unknowns. So in principle, at least, it's like you might envision being able to solve these things. Okay, so let's just say a little bit of a notation. S is going to be the number of stages of a Runge-Kutta method. Okay, and then the BI's are the quadrature weights. And then the AIJ's are these internal coefficients. Okay, so what that's basically telling you that is if you want to specify a Runge-Kutta method, there are a bunch of things it's like what you need. You need the quadrature weights, the BI's. You need the quadrature points, the CI's. And you need this sort of additional set of quadrature weights, if you will, for the internal stages, which are the AIJs. Okay, so oftentimes it's like you represent these parameters, if you will, in terms of what is called a Butcher tableau. Okay, so these sort of parameters, if you will, are if you will, represented using a Butcher tableau. And this was named after John Butcher, who is a professor at the University of Auckland. Okay, so let's just write this down. Okay, so the AIJs, it's like form a matrix, which I denote by capital A. The quadrature points, C, it's like you should think of as a column vector, and then the quadrature weights B, you should think of as a column vector as well, but it's like I take its transpose to think of it as a row vector. Okay, so component-wise, what it is you have A11 to A1S, AS1 to ASS. Okay, so you have a square matrix, it's like of the AIJ coefficients. You have a vector C1 to CS for the quadrature points. And then you have a vector B1 to BS for the quadrature weights for the final update, if you will. Okay, so let's just stop here for a minute.